Okay, welcome back to statistics. So today we are going to finish talking about confidence intervals. And I'm sorry I did the homework a bit out of order, but this will take care of the rest of what we have here. But I kind of wanted to do them out of order because they are not always the nicest order that they're given to you. Okay, so let's take a look. All right. So here we want to find what is the critical value needed to construct a confidence interval with 86%. Okay. Here's what we're trying to do. Okay. Here's our normal distribution. We want the center part here, like this bit here, we want this to be 0.86. Okay, 86%. How much do we have left over? Right, well, $1, right, minus 0.86, we should get 14 cents, yes? Okay, now, we have 14 cents and we have two pockets to put it in. So we're going to put 07 cents here, we're going to put 7 cents here. So at this point, what we need to do is we need to figure out what is this z-score here. Okay, that's what we want to find out. Right? In order to do that, that's going to be a norm inverse. Okay, so 86 in the center, because that's what they told us, right? 86%. And then we have a little bit on either side. Okay, so we're going to do norm inverse. What's the probability? The probability is 0.07. It's always a standard normal. So our mean is going to be 0, our standard deviation is going to be 1. Okay, so we have 0.07, 0, 1. And we're going to see what that gives us. Okay, it's going to give us a z-score, and I want to know what that is. Okay, so second function distribution, inverse norm. All right, and we get 0.07, comma, 0, comma, 1. All right, so there we are. This is negative 1.44757. Let's double check to see what they want this to 2 decimal places. Okay, so we're going to bring that over, so that's going to be negative 1.48. Okay, now the thing about normal distribution is it's symmetric. Okay, it's the same on both sides. All right, so if we found that here this area is 7% and the z-score that gave it to us is negative 1.8, well, if I look at the other side and I get this to be 7%, those are both positive because they're probabilities, okay? And it's going to be positive 1.48, okay? So the confidence coefficient, in order to give me my 86% confidence interval, because this right here, okay, this is 0.86 here, okay? That is negative 1 point, or plus or minus 1.48. So they just want the coefficient. They just want that number. Okay, so that's what we're going to type in. Okay, 1.48. All right. It is unlikely I would ever ask this of you because normally you're not in a position where you get to choose a confidence interval. Even if you are, the confidence intervals you should choose are going to be 90, 95, and 99. Okay, you don't really want to go out of bounds and say, I think for reasons known only to me, I'm going to go with an 86% confidence interval. Like, I wouldn't recommend it. We will talk about like how do you pick which one, but that's a chapter 9 question. It's not a chapter 8 question. All right, so we'll get to that. For now, like every problem in your book is going to say you shall construct a 99% confidence interval, or you're going to construct a whatever percent confidence interval. So this is not up to you to decide which confidence interval or which confidence level you think you should pick. Okay, and even going outside of that, like if you're going to pick like something other than the top 3, the 90, 95, or 99, like I said, in medical, the standard is going to be 99%. For most of academia, it's going to be 95%. So you can say, I'd like 96%. Like you really got to come prepared with like why. Okay, 95 is the standard for a reason. I mean, not really a great reason, but it's plus or minus 2 standard deviations. That's the confidence intervals people tend to like. So you're not on the hook to like you're going to make your own and then justify it. Okay, it's not happening. Okay, so this one, we're just going to go through this one. Okay. We have a sample size of 99. Okay. So let's go ahead and start writing some stuff down. So we have a sample size of 99, n equals 99. We're going to draw it from population whose standard deviation is sigma is equal to 39. Okay, so sigma is 39, sample is 99. Okay, not 100. Find the margin of error for a confidence level from mu. Okay, so remember we talked about last video. We said that it's x bar plus or minus a margin of error. Okay. So what we're going to have to do, right, is the formula x bar plus or minus z alpha over 2 times sigma divided by square root of n. Well, you know this and this, right? Now we got to get how do we get the confidence coefficient for 99%? Well, we just did that problem, right? We're going to have our standard normal here. We know that here, right, this whole thing, this is 0.99. How much is left? We've got 1 penny left, right? This is 0.01 is left. Okay, because it has to add up to 1. I got to break my penny into 2 pieces and put some of it over here. Okay, we'll do it that way. Okay, some of this area goes over here, some of it goes over there. How do I break the penny up? Okay, they're not really pennies. Okay, they are infinitely divisible. So I've got a ½ cent 0.005 on this part, 0.005 on that part. Okay, so what we're going to do is we're going to do norm inverse, okay, of 0.005. Our mean, right, the standard normal. So my mean is equal to 0. My standard deviation is equal to 1. So we're going to do 0 and 1. We're going to plug that in the calculator and see what we get. Okay, so the second function distribution, inverse normal. All right, and we're going to have 0.005. Okay, it's ½ a penny. Okay, and then we have a mean of 0 and a standard deviation of 1. Okay, and we ended up with negative 2.576. 2.576. Right. Some of these, like if you use the tables, you would have grown to memorize these numbers. Okay, so I knew what the answer was going to be before we started on this one. But that's how you get it. Okay, that's the confidence coefficient. All right. So to calculate our margin of error, right, we're going to do, here's the plus or minus part. So we don't need this. That's taken care of. Okay. So we have 2.576 times. Okay. What was our standard deviation? Standard deviation was 39 divided by the square root of 99. All right. That's what we're going to do. So here we have it. Right. We have 2.576 times 39 divided by the square root of 99, and you should be all set. Okay, these are all times. Well, it's 2.576 times 39. Is it 39? 39 divided by square root of 99. Okay, so we end up with 10 points. Should we just say 10.10? What do they want this as? Is it decimals? 3 decimal places. So 10.097. That's what they want. Okay, that's our margin of error. Okay, so this was 10.097, right? 10.097 here. Double checking. Looks good. We should be okay. All right. Now, if the sample size were 73, would the margin of error be smaller or larger? Okay. So, how can we do this? Let's make it a ridiculous problem, okay? So let's do 2.576 times, let's just look at the 39 over the square root of something, okay? And actually, I don't even want to do square root, okay? We've already taken a square root, okay? Which of these is going to be bigger, 10 or 2.576 times 39? And let's pretend it was 4, okay? What's 39 over 10? Right? That's like 3.9, right? I wish they would have picked an even number. But 39 divided by 2, right? What's 40 divided by 2? 40 divided by 2 is 20. So this is 2.576 times 19.5. Which of these do you think is going to be bigger? Okay. This margin of error, right? And this margin of error. So the smaller sample size, right? When n is smaller, what happens to my sample size, right? It gets a bit larger. Sorry, not sample size, margin of error gets larger. So one way you could think about this, and this is the way I usually think about it, if you have a large sample size, I'm accounting for a lot of variability, okay? So all of that's getting captured. But if I have a very small sample size, like there's more uncertainty to what we're doing. So it makes sense that the margin of error would be a bit bigger because I've got to try to capture more uncertainty about it. Okay. Now in this case, you have calculator. It doesn't say do not use calculator. And even if it did, how am I going to know, right? So this is 2.576 times 39 divided by square root of, what did they say, 73? So you could just brute force it, okay? I mean, you're learning this. This is not something we're expecting you to, like, you should know this already. Like, no, you shouldn't. You should be doing an experiment. So I guessed and I said, I think it's going to be, right? I think our n is smaller, our margin of error gets larger. So let's check. 2.576, right, times 39 divided by the square root, okay, of 73. 73, right? Let's see what happens. We got 11.758. Well, is 11.758 a bigger number or smaller number than 10.07, 10.097? I know you know this. Okay. Sometimes though, people they go on autopilot and they just keep writing stuff like this. I was like, don't do that. Okay. Because they get like the last 3 answers did that. So you have to make sure you're doing it in the right direction. Okay. So I'm not doing that to belittle anybody or try to insult anybody, or I think that you're, I don't think you're not smart or something. Like, I know you know that these numbers, how these relationships are, but sometimes when you say it out loud or when you think about it a little bit for a moment before just writing the answer down, you don't make the silly mistake of being on autopilot. And then since the last 3 numbers did it this, or did word it in this way, get this one and you forget. Okay, so that's it. It's just one of those things that students tend to make a mistake on this, something like this. It's just because the last 3 problems did it a different way. So it would be a larger sample of a larger margin of error, right? Because the sample size is smaller. 73 is a smaller number than 99. Our margin of error went up. All right, there we go. By the way, I don't tend to ask this particular question on a quiz because I know that it can be a bit confusing. So if it took you 1 or 2 times to get through this one, okay, you're in the right spot. Okay, this is not an easy problem for most people. All right. Did we do this one? I think we did this one. No, we did not. All right. How large of a sample. Okay, this is the only thing, it's the only question anybody ever cares about. Okay, how big does my sample have to be to see a result? Okay, so this one, what we're going to do is we're going to say we have a margin of error. I'm just going to abbreviate it M. Okay, and remember, it was mean plus or minus the margin of error, right? That was the Z alpha over 2 times sigma over the square root of N. Okay, so M equals Z alpha over 2 times sigma over the square root of N. Now, we're going to do a little bit of algebra here. Okay, we're going to say solve for N. All right, so what I'm going to do, Z alpha over 2, this is one number, right? Z alpha over 2. I know it looks like a couple of symbols, but it's one number. Okay, remember the alpha over 2 is telling us which column to look in if we were still doing this on tables. Okay, so it's not an operation here. Okay, it's like which one. Okay, I might as well have called it the orange column. Okay, these aren't, it says it's a number, but it is not really a number. Okay, divided by square root, or divided by that. So what I'm going to do is I'm going to multiply both sides by square root of N. So we're going to multiply by square root of N, right? We're doing the same thing on both sides. They cancel on this side. All right, so we have square root of N times M is equal to Z alpha over 2 times sigma. And now we're going to divide by M. Okay, so the M's cancel. So we have square root of N is equal to Z alpha over 2 times sigma divided by M. All right, last thing we're going to do is we're going to say, well, we got to solve for N, so how do I get rid of a square root? We square it. So we have N is equal to Z alpha over 2 times sigma divided by M, all squared. Do not memorize this formula. I will happily put this one on the quiz if I ask you a question that's going to deal with it. Okay, so you're not on the spot to memorize this. You're also not on the spot to memorize this one. I kind of wish you were, but this is in your calculator. All right, I may also put this one if I'm going to ask you to like do something here. You know, you need these pieces. I will happily write down confidence interval equals this thing. Okay, so you don't have to memorize this. You certainly don't have to memorize this one. Okay, I mean, ever since I started teaching this class, this has always been given. All right, so don't look at that and think I'm going to have to know this. Like, no, you just have to know how to use it. Okay, which is hard enough. Okay. So we have a population standard deviation of 17.8. Okay, so our standard deviation here is 17.8. What do they want to know? So how large a sample must be drawn so that an 80% confidence interval for the average will have a margin of error equal to 3.1. So my M is equal to 3.1. Now I got to figure out, like, what is this confidence coefficient going to be? It's an 80% confidence interval. Yeah. Way to go, book. Make a liar out of me. So this bit in here, right, this is 80%. How much is left? Well, 1 minus 0.8 is equal to 20 cents. So what I have to do is I have to put 20 cents in these two pockets. We're going to put 10 cents here. We're going to put 10 cents there. Okay. So in order to get that confidence coefficient, what we're going to do is we need to do a norm inverse. Okay, or inverse norm. What percentage do I want? I want 0.10. What's my mean? Well, it's a standard normal distribution. So my mean is 0, and then my standard deviation is 1. Okay, standard normal, that's always what it is. Okay, so we're going to go ahead here. We're going to say, well, we need inverse second function distribution. We need an inverse norm. We want to put in 0.1 because that's my probability. Okay, 0, 1. Enter. Okay, we get negative 1.28. Okay. All right, so what we're going to do is we're going to just calculate this this value here. We're just going to plug these things into this formula. So we have n is equal to confidence coefficient times standard deviation divided by m squared. So n is equal to 1.28 times what was my standard deviation? 3.9, I believe, in this. Was it 3.9? What was it? Population 17.8. Oh, that was way off. 17.8 divided by what margin of error did they want? They wanted a margin of error of, looks like 3.1. Okay, we got these because they told us. Okay, they got this one because they said 80% and then they left it up to us. Thanks. And then we're going to square. Okay, so what we're going to do to put that in the calculator is we're going to say 1.28 times 17.8 equals divided by 3.1. Okay, so all that is just a fraction. Okay, we haven't squared it yet. So the next thing I'm going to do is square it. Oops, I don't want to do that. I want to square it. Okay, and then equals. Okay, so n is equal to 54.0117 and some stuff. All right. Now, a lot of times we'll say round. I don't mean round. I mean we're going to boost to the next integer, the next whole number. Okay, so my n is going to be 55. It's like, wait, it's 0.01. Like, we're not rounding, we're boosting. Okay, if you want to write this properly, and you don't have to. In math classes, we use this function, we use this operation that's called ceiling, which says boosted to the next integer. Okay, if you never write this, that's fine. If you say, well, that's kind of cool, go ahead and write it. Okay, but this boosts it to the next integer up. Okay, so 54 point something is 55. Okay, pretend you're if you are pricing something in a convenience store. Say they the price came in, like you do the calculation, it should have come out to be $54.02, right? Rounding. Like it ain't $52, it ain't $54.02. It's at least $55.99. Okay. So we're just going to boost it to the next integer. Okay, and that's how we're gonna solve this problems. Okay. So what we need is 55. Okay. So double check. Yep, there we go. Okay, if the required confidence interval were 98%, would the necessary sample size be larger or smaller? Okay. So if we wanted to look at this, I want to go back to my piece of paper here. Okay. If we wanted to use 99, oh, how about that here? Okay, 98%. With the sample size be larger or smaller. Okay. So I think that's what they're asking here. Oops. Okay, everything else is the same except for sample size. So margin of error is the same, but we're going to see if we can't change confidence interval or change, move it to this one, and we're saying what would happen to what happened there. All right. So my n is equal to z alpha over 2 times standard deviation over margin of error squared. Okay, so the calculation we just did, okay, was n is equal to 1.28 times 17.8 divided by the margin of error, that was 3.1. Okay, and this was for an 80% confidence interval, wasn't it? Okay, so this was 80%. I went over here, like, I don't exactly know what this is going to be. We could figure it out, but times 17.8 divided by 3.1 squared. Okay, but do you remember when we first started talking about confidence interval, and if I said you didn't have a lot of confidence if your confidence interval was kind of a narrow one? Okay, this would be a low confidence. And do you remember what was happening? Like every time we raised the confidence, like this got a little bit bigger. What's happening with that? That's this z-score, this z value here. Sorry, not z-score. This z value here, this confidence coefficient is getting bigger. So in order to make this a wider target, my z has to be going up. Okay, let's write it a different way. The z here has to be going up from the previous one. The confidence coefficient has to be going up from the previous value. Okay, so if I make this bigger, right, it's just got to be bigger than 1.28. Like, what if it was 2? Is my n going to be bigger or smaller? Right here, my n was 55. If I plug in something new here, instead of 1.28, if I plug in 2, what's going to happen to my n? My n is going to get bigger. Okay. Now, you don't have to, you don't have to do that. You can just say, well, what if it was 95%? I know that value is 1.96. So if I put 1.96 in here instead, we're going to get a larger number. Okay, rather than having to go through and get 99% from the inverse normal thing. Okay, if you look back a couple of problems, you can say, wait, was it at 2.576? Yeah, it was. And if you remember that, that's great. Put that in here, see what happens. Okay, but we're trying to get you, like, think about what's going to happen first. And then you could write that off to the side. And then see if you can get the number and then verify what your thought was. Okay. Okay, the necessary sample size is going to be a larger weapon because the confidence interval is higher. All right. Very good. All right. I think this was one that we had done before. It was 4 or 5. They're effectively the same problem. Oh, we did 5. Okay. We did 6. I remember the cholesterol one. Here we go. All right. Here we have, we're going to choose a different options. Okay. We have a random sample of 8 Samsung Galaxy smartphones being sold over the internet, 2013. That's ancient history. And they have the following prices. Okay, standard deviation. And we want to say perform the following. Okay. So what we're going to do is we're going to say this is 199, 169, 385, 329, 269, 149, 135, and 249. All right. And they told us, right, because this is chapter 8.1, they have to say, what's the population standard deviation? Okay. Population standard deviation was 81. Okay, they'll let us calculate that ourselves in the next section. Okay. But for now, they have to tell us this. All right, perform the following. Explain why it is necessary to check if the population is approximately normal before dealing with the confidence interval. Well, we are estimating X bar, right? This is what we're trying to find. And then we have a plus or minus. This is from a normal distribution. So if I'm going to say X bar plus or minus something from a normal distribution, this has to also be normal. Okay. Now, do you remember from the chapter 7 where we had central limit theorem, right? And we had to say, well, if it's bigger than 30, right? If n is bigger than 30, then X bar will be normal. Okay, then X bar is normal. Is n bigger than 30 here? No, it sure ain't. 1, 2, 3, 4, 5, 6, 7, 8. Doesn't look like it. 8 is not bigger than 30. So in order for us to ensure normality, right, between the X bar and the being able to use Z here, because it's normal, we have to know that X bar is normal. Okay. And one way that X bar is normal is if X is normal, that would be these guys, okay, the prices. Then, regardless of sample size, X bar is also normal, okay? So we have to make sure that everything is kind of fitting in the same category here, all right? Otherwise, there's other confidence intervals that deal with other distributions to give you confidence coefficients. We don't work with any of those in this class, okay? But we do want to make sure, and this is, well, we work with one other one, okay, which we're going to do at 8.2. But we need to make sure that it's normal so that this all kind of fits into the same category, right? So why is it necessary to check? Boy, that's nice to you. It's necessary to check if the population is approximately normal because sample size is less than or equal to 30. Okay. All right. They give us a dot plot. Okay, we did this in chapter 2, but they give us a dot plot. I don't know why they do this to you. There actually are tests to see whether or not it's normal, rather than like it depend on you to eyeball it and say, yeah, it looks pretty good. Like, how are you supposed to know? This is your first time doing this. But they expect you to look at that and say yes. There's a couple of times where like there's an obvious outlier. You'll get a couple of dots. And then you get like one way over here. Okay, that's the only time you're going to say, it looks a little suspicious to me. Okay. Other than that, there are tests that you do that you learn in a different class to see whether or not these are normal. Okay. I'm not going to put one like this on a quiz where it's like, it's up to you to figure it out. Like, that's not fair. Okay. There's certain things about your book that I like, and then there are certain things where it drives me nuts because they expect you to do this. Okay. So we're going to say it is reasonable to assume that a population is approximately normal. Like, why? Because we don't have an obvious outlier, or we don't have an obvious like grouping up anywhere. Okay, so we're gonna play along and say yes. If they tell me I'm wrong, I don't really have a recourse, right? There is ways to do it, but they don't show it in the book. Okay. And then, if appropriate, construct an 80% confidence interval. Damn you, 80%. Okay. For the mean price of all the phones. Actually, we don't have to worry about that because they just want us to do the confidence interval. So what we're going to do is we're going to turn on our calculators. We're going to go to stat, tests. We're going to go down to Z interval. Okay. But instead of saying stats, we're going to enter in the data. Okay. We're going to say, oh, what's in list 1? Shoot, we have to go back to stats. Let's see what's in list 1. I better clear those out. So stats, we're going to clear our lists. Okay, we're going to clear list 1, comma, clear list 2. There we go, done. And then we're going to enter these numbers into our calculator so that we can have a reasonable confidence interval problem here. Okay, so I'm going to say enter. Go back to list one here, and we have 199, 169, 385, 329, 269, 149, 135, 249. Okay. Now we're going to go back to our stat, over to tests, down to Z interval, and we selected data. What is the what's the standard deviation here? Okay, standard deviation was 81. And when it's asking you, it's like, well, you said it was data. Where would you like to find me to find all these numbers? List one, please. Frequency. If you have a lot of numbers to enter, you don't have to enter them all. Like if you have if I had 3 prices that were $1.40 or $149, I could instead put a frequency list in here as well. I wouldn't worry about this column, this row just yet. Okay, I'm not going to ask you one that's going to do that. Most of the ones I ask you guys are small numbers. What level of confidence did they want? They said 80%. Okay, so we're just going to type it in. The calculator is going to deal with what's the confidence coefficient. We don't have to know. We're just going to say calculate now. Done. Okay. Okay. So we have to read this. Okay. So our confidence interval is going to be $198.80 to $272.20. Remember what this is telling us. Okay. This is saying to us that the average price of a Samsung Galaxy cell phone is somewhere between these two numbers. Okay, and we are 80% certain that the average is going to lie between these two values. Okay, so that's what this is telling us. So the fact that one of them is not here, that's not an average, that's an individual thing. We want the average of them being in here. Okay, so what we're going to do, come down to this, and we're going to say, what do we have here? We have $198.80, 198.80. And then what's my highest one? My highest one was $272.20. $272.20. All right. So we're going to check. All right. Right. What didn't? Oh, it's prices. So I was going to use pennies. Okay. I can't help it. For prices, I'm going to use 2 decimal places. Okay. They didn't want us to use 2 decimal places, so they ought to be a little bit. Yeah, suffer. All right. We're almost there. This is effectively the same question. Okay. Same question. I've asked this question on a quiz before. And let's see. 5 times. This is the ones we did at the beginning. Let's do one more of the ones we have to type them at, okay? So, of random sample of 12 ounce. You could be upset when you're talking about milkshakes, right? Everybody's happier. We have a random sample of 12-ounce milkshakes from 13 different fast food restaurants, and each of the calories are listed below. Okay, now I'm not so happy. So we'll figure that out. Okay, so the first thing I'm going to do is go back to stat. I'm going to clear list 1 because I'm just going to get rid of anything that was there. All right. And now, because I know we're going to need this in list 1, right? If we go back to stat and tests, we go down to my Z interval here. It's going to say, oh, where's your list? It's in list 1. Shoot, I got to go make a list 1 now. Right? So we're just going to type these things in, right? So it's going to be 591, 642, 472, 473, 510, 608, sorry, 608, 608. Okay, 580, 450. There we go. 375, 504, 504, and 700. All right. So I'm just going to double check looking at these things a little bit. Okay, going up at the top. There we go. 591, 642, 510, 608, 580, 450, 613, 470. Oh, I wanted 476 there, didn't I? Okay, let's fix that. 375, 504, and 700. All right. I'm not going to guarantee we got to get this answer right now. Population standard deviation, 92. All right, stats. Go to calc, test rather. Scroll down to where it says interval, Z interval. All right, and we put it in data. Right. So what is my standard deviation? It's 92. You can find the data in list one. I'm not going to worry about that. What standard? Which one did they want? Oh, we have to go through. Why is it necessary to check to see if the population is approximately normal? Because we have fewer than 30 observations. We only have 13. Okay. So sample size is less than or equal to 30. All right. Seems like a reasonable question. Okay, here we go. So here's one of those where you could look at it and say, is it reasonable to assume? Like, this is a little bit borderline. Like, what's going on here? Why is this looking like it's looking here? But we're going to say yes. It is. Okay. Why? Because I've done the problem before and I know what the answer is. I would not ask you to do this on a quiz. All right. So we're going to check. Yeah, they said it was too. Okay. So even they said it wasn't, right? I don't have much to argue with other than I guess it looks like it isn't. All right. So I apologize. Your book likes to do that. It drives me nuts. But they want a 99.5%. Drives me nuts. They don't use like normal confidence intervals too. Okay. 99.5%. There you go. 0.995. Okay. So there we go. 2 decimal places. Fantastic. Enter. Okay. Oh, they did 2 decimal places. So 466 and 38. 466 and 38. And 609.62. 609.62. So somebody came out and said, oh, the average of the milkshake is about 700 calories. No. Or if somebody decided like, yeah, we calculated the average of the milkshakes and we found it to be 300 calories per. Makes a great diet food. I'm sure it does. We should all be so lucky, right? So like, no. Could you show me your data? Where did you find these restaurants that are serving an average of 300 calorie milkshakes? Okay, that's not a thing. It's not a good diet food. Right? So we're comparing averages. The fact that you got one that's like 700, we don't care. Okay, one observation out, 2 observations out, that's fine. We're looking for averages. Okay, so that's what we want. All right, so we'll go ahead and now check our answers. All right, hooray, we're good. So part 1, I would ask you, okay? Part 3, I would ask you. I would not ask you part 2. You don't have the tools to do this properly, and they're just like, guess. Okay, so I'm not doing that. All right. So I think that takes us to the end of 8.1. Okay, you should have enough to go through your homework with this. Don't stress too much about this. If you get it wrong, then so be it. Okay, they do want you to eyeball it, kind of guess at it anyway. So realize this is not part of like something you're going to be tested on. So if you do end up getting it wrong, it's not the end of the world. Okay, you can afford to not worry about this. I'm not going to ask you. Part 3, I will ask you. Okay, I will absolutely ask you part 3, but not part 2. All right. should be able to get your homework done. Good luck with that, and we will meet back in the next section.